Welcome to Math 158, Functions, Graphs, and Matrices. This is section 4.1. We're going to look at systems of equations with two unknown variables. Okay, so linear equations, like you see down toward the bottom of the page there, numbers 1 and 2. Basically, what a system of linear equations is, actually back up, what a system of equations is I've got two or more equations that have the same variables in them. Okay, if I've got two variables, it's probably usually like x and y. If it's only y to the first and x to the first, and those equations are linear equations. And so we're looking at a system of equations in two unknown values. So look down here where it says number 1, number 2. Those are systems of equations in two variables. Okay, x, y, and it's x to the first, y to the first, so those equations are linear. Okay, if I have two equations with two variables, two equations with two unknown values, I can solve this system and get a numeric solution for both the x and for the y. We will look eventually at three equations with three unknown values. As long as I have as many equations as I have unknown values, I can find the numeric solution for that system. Now, what I mean by a solution, okay, the solution is an ordered pair that satisfies each of the equations in the system. More easily stated, it's the point where the two lines intersect. So number 1, we've got y equals 5x minus 3 and y equals negative 2/3 x plus 14. Those are two equations. If I graph them, I will get lines. And the solution to the system is the point where the two lines intersect. Okay, there are three methods that we're going to explore in this video for solving systems. There are a couple of other methods that we'll get to later in the course in future videos, but for this lesson, there are three methods of solving the system: the graphical method, substitution method, elimination method. The elimination method is sometimes called linear combination. The graphical method, you solve the system by graphing the equations. Substitution method, you solve the system by substitution. And in the elimination method, you eliminate one of the variables by combining the two linear equations, which is why that is sometimes called combination, sometimes called elimination, sometimes called linear combination. So let's just jump right in here. Actually, no. Before I get going, let me explain to you. I'm going to show you all three methods of solution. I will, one, explain to you why the graphical method is not always the best option. In fact, it rarely is the best option. Of these three options, the better is either the substitution or elimination. There are students who I've experienced who will want to always use one method. I am going to teach you several different methods here, three, and future videos, a couple more methods, because it is not true that in every single situation, one method will be the best for everything. Okay, so in one situation, the substitution method may be better. In another situation, the elimination method may be better. And rarely, but sometimes, the graphing method will be better. I want you to be prepared for all options. Okay. Okay. Number 1, we're going to graph. We're going to graph this, and we're going to make our x and y axis. And I'm going to do this by hand rather than using the ruler and all that kind of stuff I have here on my whiteboard. Just because I want to show you what I mean by it's not a good option solved by graphing. And then if I'm going to use the technology, I'm going to use something other than the whiteboard. I'll find some better programs to use. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can actually see I'm going to have to go all the way up to 14, which is way up there. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So let's make this first equation blue. We're going to have a y-intercept of negative 3. We're going to go up 5. 1, 2, 3, 4, 5, and over 1. And now we have that blue line. We'll make the second equation green. So we're going to have a y-intercept of 14 way up here where I said. Now we're going to go down 2 and over 3 and down 2 over 3. And this is precise. And so now the solution to that system is this point right here where the two lines intersect. Of course, it should be obvious that in order to find that point where the two lines intersect, I'm going to do some guessing. I'm going to do quite a bit of guessing. Okay. Don't really want to get into that guessing, but what if What if x was 3 and y was, oh, I don't know, 12? Let's make that my guess. What would make me think it's 312? I don't know. It's a random guess. So try it in the first equation. 5 times 3 is 15, minus 3 is 12. So that works. Try it in the second equation. Put the 3 in for the x and the 12 in for the y. And is that true? 12 equals negative 2/3 times 3 is negative 2 plus 14. So 12 equals 12. So that's true. So yes, 312 is the point on both lines. That's horrific. That's really a horrific way to do this. In number 2, just to do this again, let's make our lines. And as I'm making these lines, I'm going to say part of doing this is I'm pretending, I suppose, or imagining or believing that I'm getting my spacing perfect. Everything is straight and even. Let's make this guy the blue line again. Y-intercept of 1, slope of 3, so I'm going to go up 3 and over 1. And here is the blue line. Let's make the second equation green. So we have a y-intercept of 1, 2, 3, 4, 5, and a slope of down 1 and over 4. And then now we're going to try to guess that point of intersection. I got lucky in number 1 that I just tried 312. What am I going to try here in number 2? I'm thinking maybe x is 1 and y is, I don't know, but it actually looks to me like the x is somewhere between 1 and 2. How am I going to come up with a good solution there? Okay, so number 1 and number 2, I'm showing you really how to solve a system by graphing, but also why it's not a really great method of solution by hand. So then why do I spend time talking to you about solving a system by graphing? Well, when it's necessary. And actually, some of the videos early in the course, some of the other lessons, we actually found points of intersection. It's essentially what we were doing. But I also want to show you the issues with it. But again, what do I mean by the solution to the system? What I mean is the point where the two lines intersect. If we get away from the graphing and only go to the calculator, only use our algebraic methods, which are the substitution and the combination methods, it's easy to lose sight of the fact that when we're solving a system, what we're really doing is we're finding the point where the two lines intersect. And that's really important. So notice at number 3 here, same problem as number 2. I broke down. It's not working up here in number 2. So let's just try to graph this. What do I mean by using the graphing calculator? To use the graphing calculator, what I'm going to do is go to y equals. Let's get rid of these guys. I'm going to go to y equals, put in the first equation, y equals, let's go up to the first equation, let's clear this, go up to y1, is y equals 3x plus 1. And the second equation is y equals negative 1/4 x plus 5. I'm going to do a zoom 6, that's my standard window, and there are my two lines. Okay. I use blue and red, calculator uses I use blue and green, calculator uses blue and red, who cares? What I really want to do is I want to find that point of intersection. Now from previous things we've done in other videos earlier in this course, if I go to second calc, I can select number 5, intersect. Is the blue function y equals 3x plus 1, is that my first curve? Sure. Enter. y2, is that my second curve? Sure. I press enter. Then now guess. And I just need to be closer to this point of intersection than any other, but there are no other. So I make my guess, and we get the solution here is 1.23, 4.69. I don't think I ever would have guessed that solution. Okay, using my calculator, I did the same thing here. I got 1.23, 4.69, and that's a solution to my system. Notice how much easier that is to do when I'm solving the system by graphing using the graphing calculator. If I'm solving the system by graphing using the graphing calculator, then I probably don't want to do something like number 4. In number 4, the problem here is that I don't have the equations solved for y. In my graphing calculator, I need to put in y1 equals and y2 equals. So in number 4, if I'm going to solve this system by graphing, what I'm going to need to do is take the 2x plus 3y equals 4 and solve that for y. And I'm going quickly here, not showing you my algebra, right? I subtracted the 2x from both sides, divided both sides by the 3, so I could put in y1 as negative 2/3 x plus 4/3. And now y2, I'm going to have to take my negative 5x plus 3y equals 6, add 5x to both sides, divide both sides by 3. And so y equals 5/3 x plus 2. Okay, and now I can graph those two equations, find that point, second count, number 5, the intersection, blue is the first curve, red is the second curve, guess, that's good enough, guess, and I get 0.286 and 1.523. And there is my system of my solution of my system of equations. Not a great method of solution. There are better options. Okay, so using the calculator to solve a system by graphing is fine if the equations are already solved for y, like they were numbers 1, 2, and 3. Okay, number 4, graphing is not a very good method of solution. So let's move on and look at a second. Or actually, first let's look at an example here, right? We're not going to do this here yet. This is just an example of where we might use systems of equations, okay? Break-even point. If you remember before, we talked about profit, cost, that kind of thing, right? Revenue. My break-even point is the point where my profit is 0. My revenue equals my costs. I spent this much money buying, making, producing whatever product I'm going to sell, and then I sell that product. And the amount I sell and bring in equals the cost I outlay. That's my break-even point. We find break-even points by solving systems of equations. Okay, gasoline prices. On a regular unleaded has been increasing faster or at a different rate than premium unleaded. When would I expect the two to be equal to each other? Right. That's another example of where we're going to see this. I'm going to hold off, and we'll look at solving that later. But these are just examples of places where when we might use systems equations and the solution to the system equations to solve problems. Before we do that, let's look at a substitution method. If you look at number 5, x equals 2y minus 12, 4x minus y equals 13. This is set up perfectly to do a substitution method. Now, let me do some thinking over here. Okay, let's go this way, I guess. Remember, hopefully you've seen this. What if y equals 3x plus 6? And I say to you, find y when x is 2. If x equals 2, we would put 2 in for y, and y would be 3 times 2 plus 6. 6 plus 6 is 12. We're used to taking a value for x and plugging it in. The only difference here to that concept is that x does not equal a numerical value. X equals an algebraic value of 2y minus 12. It doesn't matter. I can still take this algebraic value, x equals 2y minus 12, and substitute that here in for the x. So 4 times x, which is 2y minus 12, minus y equals 13. Notice now that this resulting equation only has one variable in it. So I can solve for that one variable. Distribute the 4, 8y, minus 48, minus y, equals 13. Now be careful, don't, add y to both sides, whatever. I've got a 8y and a negative 1y, which I can combine to a 7y. I can add 48 to both sides. 13 and 48 should be 65, right? 48 and 13 is, no, not 65, is 61. So y equals 61. And so now y equals 61 over 7. And unfortunately, that doesn't divide. But now what I would do is take that value for y and plug it. Nope, I wouldn't plug it in there. Why would I not plug it in there? Because I want to put it back into this guy where x equals 2y minus 12. I'm going to cheat and use my calculator and show you something here. 2 times 61 over 7 minus 12, 5.428. Don't do that. I want it as a fraction, right? Why can't I have 61/7 as a fraction for x for y? Let's get x as a fraction. So math, notice number 1, change to a fraction. And so that would be 38 sevenths. So 38 sevenths, 61 sevenths is the point of intersection. On the previous examples, I left them as decimals because that feature in the calculator where I did that won't change those back to fractions, but here I can. Okay, so let's look at number 6. Y equals 3x plus 7. Y equals 5/3 x plus 11. What I could do is this is still substitution. Take the 3x plus 7 and substitute it here for y. So 3x plus 7 equals 5/3 x plus 11. And somebody says, well, I don't like the fractions. Okay, fine. What's the denominator? The denominator is 3. What if we multiply both sides by 3? So 3 times 3x is 9x. 3 times 7 is 21. 5/3 x times 3 is 5x. And 3 times 11 is 33. That simple adjustment, multiplying everything by 3, eliminates the fractions. So I'm going to subtract the 5x from both sides. And I'm going to subtract 21 from both sides, dividing by 4, x is equal to 3. Now that I know that x is 3, I'll take that value, plug it back into either equation. I'm going to the one without fractions. Plug it into either one, and so y would be 3 times the x value of 3 plus 7. So y is 9 plus 7, or 16. So my point where the two lines intersect is the point 316. Okay? So that's the substitution method. I guess I got a couple more here. Not quite as much fun, though, because notice neither equation is solved for x, nor is either equation solved for y. In the previous two examples, one or both equations were either solved for x or solved for y. So what I need to do here to do solution method by substitution is I'm going to need to solve either the top equation, 5x plus 2y equals 12, for x or for y, or I need to solve the bottom equation, 4x minus y, either for x or for y. I'm going to choose to solve the bottom equation for y because it's got a coefficient of 1, negative 1 in this case, but 1. So this equation, I'm going to add y to both sides and then subtract 7 from both sides. So I have the equation 5x plus 2y equals 12, and the equation that y is equal to 4x minus 7. So what I can do is take that 4x minus 7 and substitute it in for the y. So my top equation is 5x plus 2y, but y is 4x minus 7 equals 12. 5x plus, now the 2, gets distributed to the 4x and to the negative 7. Combining the 5x and 8x is 13x. Adding 14 to both sides, x equals 2. Then that 2, take that, put it back, always substitute back into the equation. It's either already solved for x or already solved for y. So y will equal 4 times the x value of 2 minus 7. So y is 8 minus 7, or 1. So x is 2, y is 1. 2, 1 is the point where the two lines intersect. Personally, for me, I prefer that you give me the ordered pair 2, 1. I'm also okay if you tell me that x equals 2, y equals 1. I'm okay with that solution as well. Okay, either way you want to do it. So number 8, try it. Pause the video, try number 8 on your own, see how you do. What we do for number 8 is I would take the x minus 3y equals 17, and I would add 3y to both sides. So x is equal to 3y plus 17. Then I'm going to take that value of x, substitute it into the other equation. Notice we're doing substitution. That's why it's called the substitution method. So 3 times the x value, which is 3y plus 17, plus 4y equals a negative 14. Distributing the 3 to the 3y and the 17 plus 4y equals a negative 14. 9y and 4y is 13y. Subtracting 51 from both sides, 13y is equal to negative 65. Divide both sides by 13, y is equal to negative 5. Notice we've got our negative 5. We have our y value. I'm going to take that y value, substitute it back into that equation, solve for x. X equals 3 times the y value of negative 5 plus 17. X equals negative 15 plus 17. X equals 2. So my solution is the point 2, negative 5. Okay, and every once in a while I have students who say, that's a lot of work. I don't want to do that much work. It is a lot of work. It is. Get used to it. That sounded a little snarky, didn't it? Okay, you want to develop yourself to the point where you can handle doing quite a bit of work. Now, there is another option here, though, with these two. And I don't know if it's more work, less work. It is certainly different work. I think it's simpler work. Okay. Let's look at the equation. I think these are the same two we had, aren't they? Yeah, number 9 and 10 are the same as 7 and 8, because I would probably try to do this a different way. Here's another option. What if I multiplied this bottom equation by 2? If I multiply that bottom equation by 2, the top equation stays 5x plus 2y equals 12. But the bottom equation becomes 8x minus 2y equals 14. Now, do you see what I'm going to do? This method, remember, is either called the elimination method or the linear combination method, and both fit. I'm now going to combine the two equations, and that's going to eliminate one of my variables. If I simply now add these two together, 5x plus 8x is 13x. 2y and negative 2y cancels out. That's 0. 12 and 14 is 26. 13x equals 26. Dividing by 13, I get x equals 2. Okay, so I get to that x equals 2 maybe a little bit more quickly. A little bit cleaner, no doubt. Okay. However, to get the y value, I'm still going to need to substitute that x equals 2 back into one of the original two equations. Okay, I can plug that x equals 2 either into here or into here. It doesn't matter, but it's got to be one of them. Let's just put it in the top one for fun. So 5 times 2 plus 2y equals 12. 10 plus 2y equals 12. 2y equals 2, so y equals 1. So notice we got the same solution. The point 2, 1 is still my solution. I just got it there differently, maybe a little bit more cleanly. In number 10, So what I do is I need to decide, what do I want to do? Do I want to cancel the x values or do I want to cancel the y values? In number 10, it's going to be easier to cancel the x values if I multiply the top by -3. The reason I'm choosing to do this is what I want to get to is a situation where I've got either the x or the y with the same coefficient, but one of them is positive, one of them is negative. So notice here I have a -3x and a positive 3x. That's the goal. In number 9, I had a positive 2y and a negative 2y. That's the goal. So that now when I add these two things, these two equations together, one of the variables, one of the terms will cancel out. So in this case, the -3x and the positive 3x will add to 0. 9y and 4y is 13y. -51 and -14 is -65. So y is equal to -65 over 13, or y is equal to -5. Taking a sneak peek up here, that is correct. I'm still going to have to do some substitution. I'm still going to need to take that y value, plug it back in somewhere. I'm going to go there. So x is equal to the -3 times the y value of -5. I'm sorry, y. I did that wrong. I've got x minus, this equation is x minus 3 times the y value, which is -5, equals 17. So x plus 15 equals 17, x equals 2. So I still have my solution of 2, -5. You'll get the same solution regardless of which method you use, but in some cases the substitution method is better, in some cases the elimination method is better. In these two problems, I did two different ways. It kind of comes down to a personal preference, but remember, there are going to be situations where you will want each. Okay, so let's do a couple more. Notice that in the last two, I only needed to multiply one of the equations by something to get the variables where they would eliminate or cancel. In this equation, number 11, I've got a 3x and a 5x. There's no value I can multiply one by to get the other, right? So what I'm going to choose to do here is multiply the top equation by 3, the bottom equation by 2. What this will result in is a 9x plus 4y equals 29 times 3. Whoops, forgot the 3. 29 times 3, 87. The bottom equation times 2, 10x, I'm sorry, you're yelling at me. This is not a 4. That's plus 6y. Multiplying by 2, I'm going to have 10x minus 6y equals 8. So notice I have a positive 6y here and a negative 6y here. I lined those up so that they would cancel. The reason I chose to eliminate the y values, by the way, is that this is a positive, this is a negative, and I don't have to mess with the signs. But it really wouldn't matter which one I choose to eliminate first. When I combine the two equations, the 6y and the negative 6y will add to 0, so they will cancel out. 19x will equal 95, so x will equal 5. Once I have x equals 5, I take that value 5 and plug it in either into the top equation or into the bottom equation. It makes no difference. I'm going to plug it into the top one. 3 times 5 plus 2y equals 29. 15 plus 2y equals 29. Subtract 15 from both sides. 2y is 14. Divide both sides by 2. And y is 7. So my solution is the point 5, 7. Quite honestly, the reason I plugged the 5 for x back into the first equation is because this is a positive 2y, so here I'd be dividing by a positive as opposed to a negative, but it makes no difference. So let's move on to number 12. Here what I would choose to do is to multiply the top equation by 4 and the bottom equation by 5. So I have 8x minus 20y equals negative 14 times 4 should give us a 56, so it's negative 56. 5, so that's 15x plus 20y equals 105. And again, when I add these together, notice the negative 20y and the positive 20y are going to cancel out. 8x and 15x is 23x, negative 56, and 105. I believe that should be 49, right? 105 minus 56 is 49. So x is equal to 49 divided by 23. Does not divide. Don't go to a decimal. Notice here there's an issue though, right? Do I really want to take the 49 over 23 and plug it back in for x? I know many students will power through and they will do that. I don't recommend that you do that. What I recommend that you do is go back up here. We multiply the y values, the top equation by 4, the bottom equation by 5, to line up the 20y and the negative 20y so that they would cancel out. What I'm going to do this time is multiply the top equation by a negative 3 and the bottom equation by 2. What this will do is this will line things up to eliminate the x, right? So if I distribute the negative 3 here, I have negative 6x plus 15y equals a positive 42. 2 times 3x will give me a positive 6x. Notice the x's. 2 times 4y is 8y, and 2 times 21 is 42. I have a negative 6x and a positive 6x. When I add these together, those will cancel. 15y and 8y is 23y. 42 and 42 is 84. So y is 84 over 23. So there is my solution. I can either write it as x equals 49 over 23 and y equals 84 over 23, or the point 49/23, 84/23. And there's my solution. Okay, so that was a little bit more fun. I don't think it's that bad. I mean, I get the fractions, which scared me at first. But because I had the option to just go back and to solve the system again, but for the other variable, I get fractions, but I didn't have to work with fractions. Okay, so methods of solving systems of equations. So now let's look at these gas prices, right? Based on data from 1990 to 2000, the retail cost of unleaded regular gasoline may be modeled by, I'm going to write them here. Regular gasoline as a function of time is 0.035 T plus $1.16 per gallon. And the retail cost of premium gasoline may be modeled by premium as a function of time, 0.034 T plus 1.35. Notice that the premium starts at a higher price, but the regular is increasing at a faster rate. According to the models, when will the cost of unleaded regular and unleaded premium be the same? How long will it take before they're the same? So we need to solve for T. If we want to know when these two are equal, If we want to know when these two are equal, that will happen when 0.035 T plus 1.16 is equal to 0.034 T plus 1.35. So we'll subtract 0.034 T from both sides, and that will give you 0.001 T. We're also going to subtract the 1.16 from both sides, and that will equal 1.35 minus 1.16, which is 0.19. I divide both sides by the 0.001. It would take 190 years for them to be the same. So 190 years after the year 2000 would be the year 2190. That's quite a prediction to make that it will take that long, but if things don't change, that's how long it would take for those to be equal. So there's an application of solving systems. But now let's look at a couple of situations that may occur. Let's look at this system here. I think what I'm going to do is multiply the top equation by -2 so that I get a -8x here. So I'm going to have a -8x. Notice that the bottom equation has a positive 8x, so those are going to cancel. -2 times the 5y is positive 10y equals -40. Bottom equation, like I said, starts with 8x. Ooh, that's interesting. Minus 10y equals 30. Now notice what's happening here on the left-hand side. -8x plus 8x is 0. 10y minus 10y is also 0. -40 plus 30 is -10. So we have 0 equals -10. It's really interesting to see the different responses that students have here, and they write all kinds of weird things. Keep this in mind. What does the solution to a system represent? Remember that the solution to a system is the point where the two lines intersect. These two lines right here will intersect when 0 equals -10. When does 0 equal -10? Well, okay, never. 0 will never equal -10, which means that these two lines will never intersect. The lines are parallel. There are no solutions because the lines are parallel. And I'm okay with either writing no solutions or the lines are parallel. Just, try to write better than I do. So number 14, let's solve this one by substitution. The reason I would solve this one by substitution is that I got y equals this value. So I'm going to put that value in here for y. So 6x plus 2 times y, which is -3x plus 5, equals 10. So 6x minus 6x plus 10 equals 10. Something else interesting is going to happen. 6x minus 6x is 0, and we're left with 10 equals 10. When does 10 equal 10? The right question is not, what does this mean? Yeah, that's a reasonable question, but say, when does 10 equal 10? It always equals 10. What you'll find is that these two lines always intersect. There are infinite solutions. Why are there infinite solutions? Because it's the same line. It's the same line. If you solve the top equation for y, you'll get y equals -3x plus 5. Okay, those are, in fact, the same line. Right? Let's look at an application or two here. In the 3-month period, November 1st, 2014 through January 31st, 2015, Hess Corporation stock decreased from $80 a share to $64 a share, and ExxonMobil stock decreased from $96 to $80 a share. If you invested a total of $21,600 in these stocks in the beginning of November, and you sold them for $17,600 3 months later, how many shares of each stock did you buy? Well, what I'm going to do is I'm going to say that Hess, this goes crazy every once in a while, Hess is X. And let's say that ExxonMobil is Y. So the Hess stock, when I bought it, was $80 per share. When I sold it, was $64 per share. ExxonMobil, when I bought it, was $96 a share, and when I sold it, it was $80 a share. Okay. Now I invested $21,600. That means that the $80 times the number of Hess shares plus $96 for each of the ExxonMobil shares equaled a total of $21,600. The $64 for each Hess share plus the $80 for each ExxonMobil share is a total of, when I sold them, $17,600. How many shares of each did I buy? And again, notice that I have a system of equations. I've got some bigger numbers here, okay? I'm going to notice, I think, 80, 96, 21,600 all seem to be divisible by 8. If I divide them all by 8, I would have 10x. 96 divided by 8. What I'm doing is I'm trying to simplify this. Plus 12y equals 21,600. Come on, do this right. 21,600 divided by 8. And that would be 2,700. If I divide 64, 80, and 1760, each of those by 8, that's going to be 8x plus 10y equals 2,200. So what I did is I divided each of those numbers by 8 because I thought that they might all divide by 8 in order to get smaller numbers. I can decide that these numbers are smaller enough if I'd like, or I can notice that the numbers are all even, so that means that they're all divisible by 2. So I can reduce this even farther. 5x plus 6y equals 1350. 4x plus 5y equals 1100. So now I can solve the third system here because I simply reduced and gotten smaller numbers. I could have done it right from the second one if I wanted to. I went to the third. Now if I want to eliminate what? The x or the y? Let's eliminate the x. One of the equations is to get multiplied by 4. The other one is going to get multiplied by 5. Now one of them should be a positive, one of them should be a negative because I'm going to get 20x. I want one of them to be positive, one of them to be negative. Sometimes what I do is I don't worry about the negative yet. Just multiply the top equation by 4. So that's 20x plus 24y is going to equal 4 times 1350, which is 5,400. 5 times the 4x is 20x. 5 times the 5y is 25y, and that's going to equal 5,500. The reason I might do that is now, look, do I want a negative 24y or a negative 25y? You know, I think I wanted this to be negative so that this would have been negative, negative, and negative. That way I'm subtracting the smaller numbers. Doesn't really matter. Cancel. 25y minus 24y, 1y equals 5,500 minus 5,400 is 100. So y equals 100. So I'm going to take that value for y, plug it back into any one of these 6 equations, any one you want. I'm going to put it here. So 4x plus 5 times 100 is 1,100. So 4x plus 500 equals 1,100. 4x equals 600. X equals 150. So I bought 150 shares of Hess, and I bought 100 shares of ExxonMobil. Okay, so this is an example of using systems of equations to solve a problem, some application there. Okay. All right, so I believe we have at least one more. Looks like we got one more here. The demand and supply functions for your college newspaper are Q equals negative 10,000p plus 2,000, and Q equals 4,000p plus 600 respectively, where P is the price in dollars. At what price should the newspapers be sold so there's neither a surplus nor a shortage of papers? Okay, so this is the demand function. This is the supply function. In order to have no extra papers left over, in order to not run out of papers, you need your demand function and your supply function to be equal to each other. In other words, this demand function and this supply function should be equal. So negative 10,000p plus 2,000 should equal 4,000p plus 600. I'm going to add 10,000p to both sides. One more zero there. So 2,000 is equal to 14,000p plus 600. Then I'm going to subtract 600 from both sides. 1,400 equals 14,000p. If I divide that by 14,000, p will equal 0.1. So I should sell each newspaper for 10 cents. And if I sell each newspaper for 10 cents, I will have no supply and no shortage. Okay, so there's an application. Functions, graphs, and matrices, systems of two equations and two variables. Okay, using the graphing method, the substitution method, the elimination method, which is sometimes called the linear combination method. Please make sure to be practicing these, both the practice problems that I've assigned, the problem sets that you'll find at Blackboard, as well as the problems that you'll see in WebAssign.